We extend a warm welcome to this brief explanation on numerical integration, presented by Professors Diego Valencia and Bianca Miranda. During this introduction, the fundamental concepts of numerical integration, its importance, and some of its applications will be presented, with the aim of facilitating the understanding of these methods and their usefulness in solving mathematical and scientific problems. We hope this explanation will be clear, engaging, and helpful for your learning. The notion of the integral is a fundamental concept in mathematics that enables us to determine the area under a curve. To clarify this concept, let's consider the function f(x) equals x squared 2 plus 1. When plotted, this function forms a recognizable parabolic shape, with a slight vertical shift. When we talk about integrating a function like f(x), what we are truly aiming to do is calculate the area enclosed by the curve, the x-axis, and the vertical lines at specific points. For example, if we want to find the area under f(x) between x equals 0 and x equals 2, we express this as the integral of x squared 2 plus 1, with respect to x from 0 to 2. The exact value of this integral, upon computation, is determined to be 14/3. This precise value represents the actual area enclosed by the curve and the x-axis within the defined limits. However, what if we come across a situation where determining the integral analytically proves to be difficult? In such instances, we can resort to numerical approximation methods to estimate the area under the curve. One common method involves dividing the region into trapezoids and summing their areas to obtain an approximation of the total area. Initially, with a small number of trapezoids, our approximation may show significant differences from the actual area. Yet, as we increase the number of trapezoids used, the individual trapezoids become thinner, more closely resembling the shape of the curve, and converging towards a more accurate estimate of the integral's value. Tracking the transition from a few trapezoids to a larger number, such as 5, 10, 15, and eventually 50, illustrates how refining our approximation leads to a closer match with the true area of 14/3 under the curve f(x) equals x squared 2 plus 1. In conclusion, the integral serves as a method to precisely calculate the area beneath a curve, while numerical techniques like the trapezoidal rule offer a way to estimate this area by summing trapezoidal segments. As the number of trapezoids used grows, the accuracy of our approximation steadily improves, approaching the actual value of the integral. This foundational understanding of integration and numerical approximation lays the groundwork for exploring further numerical methods and the various practical applications where integrals are essential. In future lessons, we will delve deeper into these methods and illuminate the broader importance of integrals in diverse real-world scenarios. Thank you so much for watching the video.